So the next topic we're doing is mathematical induction, and basically these three steps here are to be followed in every question. You must do them, you must show evidence of them, and they solve every question. There's three main types of induction questions: addition, divisibility, and inequality. And that means, like for instance, for the inequality, there'll be a greater than or a less than sign in it. For divisibility, there'll be the word, I've just noticed that's misspelt, divisibility. I have to insert an I there. There'll be the word prove that something is divisible by something else. And then addition, you will see plus signs or minus signs. So let me just fix that up first. So the first question is, and this is an addition style, and there's pluses as you can see. Prove that 3 plus 10 plus 7, so we're going up by 7s, plus, and here's the general term, 7n minus 4, that's how you generate the series, that the addition of all that equals this here on the right hand side. So straight away we're going to set up the fact it's a left hand side, right hand side style proof. Now we've not done series before in 2 unit yet, but this is the general term. So if I sub in n equals 1 times 7 minus 4, I get the first term. n equals 2, I get the next term, etc. So that's how you generate it. This here is important. Ordinarily it starts at n equals 1, but it doesn't always. So if it's n equals 2 or something, we have to modify our proof. Okay, let's start it. So step 1, if you look back, was prove it's true for n equals 1. So that's simply proving that the left-hand side equals the right-hand side when n equals 1. So we write prove true for n equals 1. And we write left-hand side equals, the general term is 7n minus 4. So it's 7 by 1 minus 4. Whoops, change colour. Let's stop that. Can't figure out how to change that at the moment. Equals 3. Okay, that's the left-hand side, and then sub it into the right-hand side, which is n on 2 into 7n minus 1. So it's a half into 7 times 1 minus 1, which is a half, into 6, which is 3, equal to the left-hand side, therefore true for n equals 1. Step 1 done. Step 2, now as I said, this is a logic style question. So we've proven it true for n equals 1. Step 2 is assume it is true for n equals k. Any letter, but we choose k. So if we assume it's true for n equals k, step 3 is prove it's true for n equals k plus 1. So if you think about the logic of that, step 1, we've proven it's true for n equals 1. If we're assuming it's true for n equals k, and then we can prove it true for k plus 1, well, if it's true for 1, therefore it's true for 2. If it's true for 2, therefore it's true for 3. So therefore it's true for any number. That's the way the logic works. So the second one, the second assumption's the crux of the whole problem, because we use this to prove it in part 3. So with an assumption, we just write it down. You don't need to prove it. That's step 3. So assume it's true for n equals k. So what we're going to assume, and you need to write this down, is that 3 plus 10 plus 17 plus plus, and instead of n, we're now going to write a k, plus 7k minus 4 equals, and the right hand side becomes a k as well, k over 2 into 7k minus 1. So all you're doing in part 2 is rewriting the question. Instead of n, you're putting in a k. But if we can prove it's true for n equals k plus 1, therefore it's true for any number, following on the fact that we've proven it's true already for n equals 1. So step 3, it's a good idea to write down what we need to prove. We want to prove that 3 plus 10 plus 17, so everything we've got in part 2, so that's k terms, plus the value when n equals k plus 1. So if we sub it into here, it's moving. If we sub it into here, that's 7 k plus 1 minus 4 equals, do that in a minute. So what have we got on the left-hand side here? We're trying to prove it's true. I didn't write that actually. Prove true for n equals k plus 1. So on the left-hand side, we've got all the terms up to the kth term, and then we've got the k plus 1th term. And on the right-hand side, all you've got to do is sub in k plus 1. Hi, Mr. Cobb.
Hi, Miss.
Would you like to just keep going on this induction question? We're just subbing in k plus 1 over here instead of k. So what's that going to be if I change my pen?
K plus 1
instead of k. So on the top it's going to be k plus 1 over 2 and 7 into k plus 1. So you're just taking out the k,
okay, I'm
putting in a k plus 1.
Okay.
And we might, okay, is that a joke? Is that a pun?
Yeah.
We might expand this right-hand side and then we'll continue with the proof. And if we just tidy this up a little bit on the right-hand side, and we don't move it, that's a k plus 1 on 2 into, that's a 7k plus 7 under there. If I change that, it's a 7k plus 7 minus 1, so it's 7k plus 6. So this is what we're now looking to prove, that the left-hand side equals the right-hand side. We have to show that this, if we add up all this, and you've got to remember this is an infinite series, so we don't know, we can't actually add it up as we normally do. But if we add this side, that we get this answer. And once we've done that, that means we've proven it true for n equals k plus 1. Therefore, it's true for any number, because we've proven it true in step 1 for n equals 1. And if we prove it true for n equals k plus 1, therefore any k we sub in and add 1, it's true for the next number. So if it's true for 1, 1 plus 1 is true, it's true for 2. If it's true for 2, 2 plus 1 is 3, it's true for 3, and then I can go on forever. Okay? So we have to show that the left-hand side equals the right-hand side. Well, the left-hand side from the previous page was 3 plus 10 plus 17. Whoops, I don't know what that arrow is doing. Whoa, go back. 3 plus 10 plus 17 plus up to the general term plus your k plus 1th term, which we haven't expanded yet. We've got to show that equals the right-hand side. Okay. So, well, what do we know? The assumption in part 2 is the crux. If you have a look at the assumption, we assumed that 3 plus 10 plus 17 plus right up to 7k minus 4 was equal to k on 2 into 7k minus 1. That was our original assumption. So all of that, we can use the assumption that adds to k on 2 into 7k minus 1, which is your initial question. So we have to add, and I'll expand this out as we go now. So if I use blue again, if I expand the first set of brackets out, that's 7k plus 7, then we've got a minus 4 off it. So that's a 7k plus 3. So I need to show that this is equal to the right-hand side. And the right-hand side was k plus 1 on 2, 7k plus 6. So that's what we need to get on the left-hand side. So a common denominator of 2 gives us k, 7k minus 1, plus 2 outside of 7k plus 3. Okay, so it's 7k squared minus k plus 14k plus 6 all over 2, which equals, equals 7k squared plus 13k plus 6 all over 2. Now if I look at this, that does not look like that, does it? What do we have to do? Well, we might have to factorise the top. Basically, the answer's there. Hopefully it does factorise as this, as k plus 1 and 7k plus 6 all over 2. You just check that's correct, which it is, and then you write equals the right-hand side. Now I'm going to rub this out for the moment. Can I rub that out? No, I can't rub that out. Not sure why I can't rub that out. Okay. Now, if you look at old solutions, past a couple of years ago, they used to make you at the very end write a very big paragraph. Essentially something like, as the statement's proven true for n equals 1 and the statement was assumed true for n equals k, we've proven the statement true for n equals k plus 1, thus if it's true for 1, it's true for 2, it's true for 3, and so on. They don't make you write that anymore. All they make you say is, as proven by mathematical induction. Induction. It's not great, is it? However, that's an addition question.